It is a joint work with you, a long-standing one. But hopefully this year, we are going to submit it because it has come to its end. So let me see. Well, I'm going to say some preliminaries, very few, because this talk is addressed to you mostly. And then I will go through the proof that we have done about the two cases that we have to distinguish in order to have our findings. So we start from a metric space, XD, and the equilateral dimension of X is the maximum number of points that are all at equal distances from each other. This dimension, the equilateral dimension of an n-dimensional Euclidean space, is always n+1 if the dimension is n. And this is achieved by a regular simplex. And if you are on an n-dimensional vector space with the L infinite norm, then you have equilateral dimension 2 to the n, achieved by a hypercube. However, if we go to the L1 space with the Manhattan distance, then the equilateral dimension is not known. There is this Kushner conjecture that states that it is exactly 2n, and it is achieved by a cross polytope, but it's not known if it can be more than that. So right now we see equilateral dimensions of norm spaces. And from all those known spaces, perhaps the easiest one to handle is the LP spaces, the Lebesgue spaces. So there are things known about them. If P equals to 2, if it is a Hilbert space, then the dimension is n+1. And if P is greater than 2, then the dimension is greater or equal to n+1. And there are sorts of Kushner's conjectures about that, but I don't want to delve into any of that. So there are various results for arbitrary norm spaces. And for n-dimensional Riemann manifolds, we have an underlying metric. We also have that the equilateral dimension is n+1. So what we are going to deal with is with a space which is not a norm space and it is not a manifold. So this is the Heisenberg group, and we consider the Heisenberg group equipped with the Korani distance d, which I am about to say what it is in a while. So the Heisenberg group is actually C times R with group law, ZT star WS equals to addition in the first coordinate, complex addition, Z plus W. And then we have this peculiar thing in the real coordinate is T plus S plus the standard symplectic form of C. So two image of imaginary part of Z W bar. So we have this Heisenberg norm, which is not a norm in the usual sense. So Heisenberg group is not a norm space, but it is customary to say that this thing is the Heisenberg norm or the Korani gauge. This is given by, by this thing. The gauge of ZT is the Euclidean norm of Z to the square minus IT. And this is it. And with this Korani gauge, we define the distance like that. I'm not writing down the actual formula. It is pointless. But there are things that I can say about this distance. This is one of the two standard distances that can be defined in the Heisenberg group. So this invariant under the left translations of the Heisenberg group. Under the rotations about the vertical axis and under the conjugation, all these transformations are known as Heisenberg isometries. And also it is scaled up to multiplicative constants by the action of the Heisenberg dilations, which is ZT goes to RZ R square of T, when R is different from 0. I have included here the negative values. There's no problem with that. So we have the similarity group, which consists of all those transformations, and it is actually the product of the Heisenberg group times R positive, and is comprising of all the above transformations. Now, this metric is not a path metric. And also, there is no Riemannian structure in H with underlying metric D. So it is a very peculiar situation. In contrast to this, I have to say that the Carnot-Carathéodory metric is a sub-Riemannian distance, but we have the same thing here. We don't know too many things about equilateral dimension in sub-Riemannian manifolds. So in some sense, this is a first attempt to approach the problem in the sub-Riemannian case somehow. Now, I was talking about the Carnot-Carathéodory metric, corresponds to its sub-Riemannian structure. And our main theorem, as it is right now, is that the equilateral dimension of the Heisenberg group is greater or equal to 4. Okay, our main goal is to prove that it is exactly 4, that is n plus 1. And this also will tell us that the equilateral dimension of the Heisenberg group, of the first Heisenberg group, it is equal to its Hausdorff distance. I don't want to go into the details of the Hausdorff distance and the topological distance. It's not in the purpose of this talk. So this is our theorem as it stands now. We will see that there are two cases. In the first case, we have proved the sharpness of 4. In the second cases, we are very close. Okay. So we can assume by applying any similarity that the common distance is 1. And any 2 points with distance 1 can be mapped via an element of the similarity group, either to the points, these points, who lie on the vertical axis, 0, -1/2, and 0, 1/2, or these points, 0, 0, and 1, 0, which lie on the complex plane. And this is, I will explain in brief. In the first case, P1 and P2 lie in an infinite C circle. That is a circle who has an end at infinity. And in the second case, P1 and P2 lie in the finite C circle, which is a Euclidean circle. And it is centered at 1/2 and has a radius 1/2, which is as it is. So this happens because any 2 points in the Heisenberg group lie in a C circle. Therefore, P1 and P2 either lie in the same infinite C circle or in the same finite C circle. And the question is why we have to distinguish the two cases. The two cases have to be distinguished because infinite C circles and finite C circles are both G invariant, but there is no element of G that can map an infinite C circle to a finite C circle or vice versa. So it is imperative that we must distinguish the two cases. Okay, and we shall treat all those two cases separately. In the first case, where 2 points lie in an infinite C circle, we have our proposition that the maximum number of equidistant points in H, such that 2 of them lie in an infinite C circle, is 4. So this is sharp. And I will show you a modified proof of that. I like it more, but we have the other proof that we have, it is okay as well. So if we have these 2 points on the vertical axis, then all points of the Heisenberg group, which are equidistant to both of them, must lie in the plane, in the complex plane, t equal to 0. Those points of the plane, such that d of p of the distance with distance from both p1 and p2 equal to 1, lie in a planar circle, which is this one, the circle center at 0 and of radius 3/4 to the 1/4. So we have this thing, and we only have to prove that this particular curve cannot have more than 2 equidistant points. So this is what we're going to prove, that there exist at most 2 equidistant points in C3 inf, as I have denoted this thing. So I start from a specific point, and then I find by making calculations that there are exactly 2 points that have a distance 1 from this point. I calculate, okay? I have omitted the calculations, but you believe me, we have done so many calculations, so there's no problem for that. So we have this image for this particular triple of points, but observe that the distance of those Q plus and Q minus, if you go down and calculate, is not 1, can never be 1. So now the argument is the following. Since there can be no equidistant triple of points containing P0, this triple must necessarily contain Q0 plus minus, which is a contradiction. And suppose now P is arbitrary, then we rotate. There exists a Heisenberg rotation, R, such that R of P equal to P0. And I write down Q plus or minus the inverse image of Q0 plus or minus. And these are equidistant from P. But now, on the other hand, this is not the distance of Q plus and Q minus cannot be 1. So there can be no equidistant triple in this Euclidean, in this C circle, which by the way is a Euclidean C circle. Euclidean circle, I'm sorry. And this is the proof, which is very, very easy and very straightforward. But when we go to the other case, things get a little bit complicated. So let's go to the other case. And we first assure the existence of triplets of equidistant points. And our proposition is that there exist triplets of equidistant points in H, such that 2 of the points of each triple lie in a finite C circle. How do we do this? We have done it in many, many ways. So this is one way, but I think I will change it. So if we take the points to lie in this Euclidean circle on the plane, then any point equidistant from those 2 points must lie in the intersection of the surface of the bisector, actually, which is defined by this equation, and the Korani unit sphere, this one. So now I take advantage to describe this. I can do it with Cartesian coordinates, but it will be a mess. So something that will produce a bit of less mess is, now I write this intersection as the curve C3 fine, whatever. And an alternative description is it is the intersection of these 2 spheres, 2 Korani spheres. This thing. So maybe the plot is not very, very accurate, but the curve is this guy. So you see the unit sphere is actually, it's quite like a usual sphere, but the Korani sphere based at 1, 0 is something like a pill for coronavirus, something. Okay, so, so the trick we have done is to consider the Korani-Riemann spherical coordinates. And we did it by restricting them into -p/2 pi/2, which was correct. So these are the Riemann spherical coordinates, and I'm writing down the previous equation. I'm just making calculations. There are other ways to produce this thing quickly, but this is the way we have written it so you don't get confused. So this is the thing, and plugging in, we obtain after this trigonometrical things, blah, blah, blah. We obtain this. This is the parametric equation of the curve C3 fine. Okay, so we have the plot here in the theta phi plane. So these lines are the lines pi over 2 minus pi over 2, pi over 2. So we were correct to restrict theta and phi in this way. So we want to delve into that and to write down a parametric representation of this curve, which is not implicit. So we take this this equation, the implicit equation, and we write it like this. So we have to solve in terms of cos. We have to eliminate the cos. So the in this way, this fraction, we put it a function of theta. We have done all that and checked and triple checked and double checked thousands of times. So this function is an even function defined in this closed interval, and theta star is this r cos of 5 over 2 minus square root of 6. And attains its global maximum value at 1 at those points, at the end points. Attains a global minimum value square root of 5 over 8 at points plus or minus r cos of 1 over 4. And also attains a locally maximum value 7 over 8 at 0. This is the function. And we have draw it in the same plot as the curve, so we see how it behaves. So actually the function starts from here. Those two things do not belong to the function we want. So this is it. Okay, so we can write down a parameterization. The curve C3 fine is the union of the graphs of the functions phi plus minus defined on this interval, closed interval I, where phi plus minus theta is minus theta over 2 plus or minus r cos f of theta. So I go back to the plot. So here we are. I mean, this is the one part of the curve, and this is the other part. And so we have parameterized this part and this part. Theoretically, we can start from any point and write it down as the union of two parts, but we will see a little bit about that a little bit later. Okay, so towards our proof, we are going to study some obvious symmetries of C3 fine. I have to say here that the previous curve, the circle, has a lot of symmetries besides the rotation. And all the symmetries come from the conjugation zt goes to z bar minus t. But here, as we can see from the plot, we cannot expect that any rotation preserves the curve. Maybe preserves some points, but not the curve. And this is in contrast to the previous situation where a full rotation of the Heisenberg group preserves the whole curve. Here, this cannot be done. But here we have a lot of involutions that preserve the whole curve. The first involution, which comes from zt goes to z bar minus t, is the antipodal involution, which takes, this takes a point with coordinates theta phi into minus theta minus phi, which is again, so it is an involution of the curve. So if we take a point upstairs, it goes to the symmetrical point downstairs, and so on, and vice versa. And this is the antipodal involution, and pairs of points of this sort will be called antipodal points. So we now study the function of a distance between a point and its antipodal point, and this produces this terrible function. Okay, so that's it. So the following hold for this function: it attains a global maximum at 3 pairs of antipodal points, which are those. And these points have also another property that we are not going to talk about. They are points of horizontality, okay, but that doesn't matter. So the global maximum value is 15/4, and the global minimum value is at 3 pairs of other antipodal points, which are these things. So that's quite repulsive, yeah, which you have checked again and again and again. But the most important thing is that the distance of a point from its antipodal is always greater than 1. In fact, we have shown that the distance of pair of antipodal points lies between 1/1.378 and 1.391, which is quite impressive if you think about it. A very, very small gap between these two values, but actually both of them are strictly greater than 1, which is something that we are going to take advantage from. Now, we have 2 other symmetries. Now, this is the antipodal function. Actually, we care about this part of the function, this one, this thing. These other 2 blue legs do not concern us because here we have the curve. And it goes like that. Anyway, so next is the symmetric involution. I have put names on that. So the symmetric involution takes a point theta phi to the point minus theta phi plus theta. Okay? And it is symmetric because it is symmetric with respect to the point 0, 0. This is why I named it symmetric. Okay? So this is the symmetric points. And again, we study the distance of the symmetric points. Here we have some interesting facts. First fact is that this function is very easy. It's 4 1 minus cos theta to the squared, so it's something that we can handle very easily. This is it. So you can see that it produces points with distance 1. We don't care so much about the greatest value, the maximum and the minimum value, but we care about points with distance 1. And actually, it's attained the global maximum value here. And but the important thing is that it determines 2 pairs of symmetric points. These are those. So with this, we already have found 4 points in the Heisenberg group that they are equidistant. So actually, the proof of our theorem in the beginning can already stop here, but we go on into our study. So these are the points. And also by taking the composition of the previous 2 involutions, we find a vertical involution, which is very important because if you see what this involution does, it takes a point theta phi to the point theta something else. That means that it takes a point to the same, to another point which lies in the same Euclidean circle. So this is important. And again, this also does this thing. And we have that all these conditions hold. So G1, G2, the symmetric, the vertical, and the antipodal involutions are clearly related to each other by those relationships, those relations, I'm sorry. And again, we take the function of a point and it's vertical. And this is this monster, which is not a monster actually, but it is full of cosines and squares and cubes and things. But in any case, it can be drawn by very nice online plot software. And this is it. The vertical function. We care only about this part of the function. We don't care about those two legs. And you see, if I take one here, you see that there are points that attain the value 1. And actually, we can say about this function that it attains its maximum value 15/4 at 0. And also determines, again, 2 pairs of symmetric points whose distance is 1. Now, this theta 0 is some cubic root, some root of some cubic polynomial in cosine, but it is almost 1.135. So we have 2 points here. So you see we have 2 points that lie in the same Euclidean circle which is parallel to the complex plane, okay? Because any 2 points lie in Euclidean circles, it's a C-circle. Okay. So from the symmetric and vertical involutions, we have already established the existence of equidistant quadruples of points, which are such that 2 of them lie in the same finite C-circle, and we can stop here, but we have done a lot more than that. So our next proposition shows that something much stronger holds. And it is that if you fix a point for any point in the curve C3 fine, there exists at least one point such that it has distance 1 from your fixed point. So actually, there exists at least 2 is the correct statement, but let's see the proof and we will see all that. So fix a point and consider the function of the distance from that point. Okay. And the function is continuous and bounded in both branches of the curve from P0 to its antipodal point. There are always 2 branches. So since the function, since the distance of a point from its antipodal is always greater than 1, we use the intermediate value theorem. So we find that at each branch, there exists at least 1 point such that the distance of this point from P0 is 1. So what do we have? We have any given point, and we have 1 point in one branch and 1 point in the other branch. We have distance 1. Yeah. So our thing is to prove that this triplet cannot be equidistant. I mean, these 2 points that we find cannot have distance 1. So what is left to prove? I'm about to finish very soon, so it will not take long. I have some ideas, but I think that the second idea is the one that works. As in the main proposition, the function attains the value at most twice. If we can prove that, we are done. And then it's equivalent to say that every Korani sphere centered at P0 and radius 1 intersect the curve at most twice. When they lie in the same Euclidean circle, which is parallel, intersects at most 1. But this can be quite confusing. But then one has to show that this point of intersection cannot have distance 1. This is the one idea that I have, which is so that we avoid all those terrible calculations that we have to bear under this Korani-Riemann coordinates. But a different argument is the following. Suppose that you have 3 points in your curve that are equidistant. So you have a sort of equilateral triangle with vertices on the curve. Now there exists a Euclidean circle passing through these points, always. A Euclidean circle is a C-circle. So you can map the C-circle to a circle in the plane, and so that you cannot have this situation there, and you're done. So I am almost certain that this is how we can fix the proof and finish this long-standing problem that we have, and maybe next time drink coffee without having this problem, but having another one. So that's it. I don't have anything else to say. So